This is the photoelectric effect simulation I sent you, but you might not be able to access it on your phone, so you can watch this video. What I've got here is a metal plate, and on this metal plate there are obviously lots of delocalized electrons. That's what you've got on a metal. And at the moment this is sodium. You can change the metals, we'll do that afterwards. But for now I've just got a little bit of sodium here. And what I'm going to do, I'm going to shine some light on it. And I'm going to start off with some red light. And I'm going to increase the intensity. Intensity just means how bright it is. Now what that means in terms of photons is the number of photons being emitted. So if I've got a low intensity light, which you'd sort of think of as darker, it's emitting less photons. If I increase the intensity of my light, then I'm emitting more photons. Now at the moment I'm shining red light. Red light has got a long wavelength, which means it has a low frequency. It's a low frequency light. It doesn't have much energy either because of the equation E equals HF. If F is low, the frequency is low, which it is for red light. If F is low, E is low. So these photons are low energy. And I'm shining these photons onto these electrons here, but the photons don't have enough energy to emit the electrons off of this surface. But what happens if I start to increase the frequency of the light? Now, increasing the frequency means decreasing the wavelength. So I'm increasing the frequency of the photons. Increasing the frequency increases the energy, and more energy the photons have, the more energy they give to the electrons, and eventually I get to a point, you can see I get to a certain frequency where the light has now got enough energy that it can emit the electrons off of this surface. If I increase the frequency further, if I keep increasing the frequency and keep on increasing it, you can probably see what happens. The speed of the electrons, or the kinetic energy of the electrons that are being emitted, is increasing. And if I go all the way up to very high energy UV, you can see the electrons are being emitted with loads and loads of energy. And this graph over here is showing what we've been doing so far. When the frequency was below a certain value, the energy of the electrons was zero. The electrons weren't being emitted from the surface. But when you get to a certain frequency value, which was about this sort of greeny light here, this greeny blue, at this frequency here, there's just enough energy in these photons to cause these electrons to be emitted from the surface. But they don't have a lot of kinetic energy once they get emitted. But if I increase the energy of each individual photon, then I get much more kinetic energy in those electrons that do get emitted. These electrons that are emitted are emitted by photons hitting them, so they're called photoelectrons. A photoelectron is just what we call an electron that has been emitted by a photon hitting into it. Now, what gets really interesting here is if we look at the relationship intensity has with this. This is something that sort of caused this sort of quantum physics, or this idea of photons being little packets of light to be invented, or to be thought of. If I have very low frequency light, but I have loads of it, so look at this. I've got loads and loads of photons. Sure, each photon is low energy because it's red, it's low frequency. Even though I've got loads of these photons hitting into the electrons still aren't gaining enough energy to jump off. And that's because the photon and electron interaction is a one-to-one interaction. An electron can't store up the energy from lots and lots of photons hitting into it. It can't accumulate the energy of multiple photons. It's a one-to-one. It's whether or not one individual photon can give enough energy itself to the electron to cause it to be emitted from the surface. And in the case of the red light, there's just not enough. Now, if I go to only 1%, so a really small number of photons, but this time I make each photon high energy. There we go. So here we can see that although I'm only throwing a very small number of photons at the metal, although only a very small number of photons are hitting the metal, I'm still getting some electrons being emitted. And that's because now each photon has got enough energy to emit each electron and also give it a hell of a lot of kinetic energy once it gets emitted as well. The analogy I like for this is thinking about, imagine a coconut sitting on top of a little stand thing. A coconut standing up, one of those things you get at fairgrounds, you have to throw the ball at the coconut to knock it off. If I tell you, try and knock off that coconut, but I give you only ping pong balls, which are very low energy, a bit like red photons, you can throw 1,000,000 ping pong balls at the coconut, which is like the electron. You can throw 1,000,000 ping pong balls at the coconut, you'll never knock the coconut off. It doesn't matter how many ping pong balls you throw, it's not going anywhere. But if instead of ping pong balls, I give you tennis balls, which are a bit like our high energy photons, then you're going to be a bit more successful. Because those tennis balls have got more energy to give to the coconut to knock it off. So that's an analogy I quite like. Now, if we use different metals, we'll see we get different energies needed to lift the electrons off of the surface. Well, it needs to be quite high energy. No visible light will work for zinc. In fact, it looks like we need a bit of UV light, sort of halfway in the UV range. So zinc holds on to its electrons much more. So we would say it has a higher work function. The work function is how much energy is needed to emit an electron from the surface, to emit a photoelectron from the surface. And different metals have got different values for this.